which is going to be still section 7.3. And what we're going to look at this time is solids of revolution. So we've had a little bit of experience, as I mentioned yesterday, with solids of revolution in terms of taking a slice and revolving it around a line of some sort. And we ultimately know that the gist of it is that instead of having a two-dimensional situation where we have an area that's found by summing up rectangles, okay, what it boils down to is that we're going to have a volume that's going to be found by summing up cylinders. Now, we've only seen the cylinder issue because that's all we've done so far. We've just done cylinders only. Okay? As it turns out, there's going to be a little bit more to it than finding the volumes of cylinders. And the bottom line, I guess we started with cylinders because that's the easiest variety, I guess. So we're going to look at several different problems here that are going to involve the following example. And we're going to keep it simple here and just generalize from there. We're going to just do one arch of the sine curve. So we're going to go 0 to pi. We know that y equals sine x is a fairly easy function to deal with. And we're going to take that area, and what we're going to do with that area between the sine curve and the x-axis, so ultimately our, if you will, if our shaded region is this, okay, what we're going to do is we're going to be asked to take that region and revolve it around the x-axis. Okay? So if we had to revolve it around the x-axis, let's think about what that would look like. If I took that shape and I revolved it around the x-axis and made a three-dimensional shape out of that, okay, it would be almost spherical, wouldn't it? Not quite, really, because it's going to be a little taller at the top, so it would be like and it really wouldn't be kind of long enough, I guess, to be like a football shape, I suppose. But again, if we revolve that around, we're going to get this three-dimensional shape. Now, like I said, whether you can visualize the final shape or not, well, it doesn't really so much matter. The key issue, though, is that if we're going to find the volume of such a solid that's revolved around the x-axis in this case, okay, what we want to do is we want to just think about one slice. So if I were to take one slice and make it a vertical slice, okay, taking that rectangle and revolving it around the x-axis is just like we did before. It's going to be a cylinder, isn't it? Okay? And if we get a cylinder as such, okay, then we call this the disk method. So when we find the volume of such a solid and the slice that we choose creates a cylinder, then we're going to use what we call the disk method. All right? Because the slice that we have is a disk. Now, when we use the disk method, the key issue here is recognizing that, in fact, when we do that slice, that we get a cylinder, and the fact that that cylinder's area is always going to be pi r squared h. Right? Now, if I were to take this individual slice and look at it in 3 dimensions, keep in mind that it's going to be, have some kind of shape like that, basically. It's going to have a radius. It's going to have a thickness, which is ultimately going to be the height. And so for us, the question is, just like we did in the problems from yesterday, can we write an expression, okay, related to x here that is going to replace our r and our h? Okay? So let's see if we could do that here in this case. So knowing that I'm going to have r squared here, if I look at this picture, remember the culmination of this is the disk is going to come down into this area because the whole entire slice is going to be revolved around the x-axis, and so therefore our disk would look something like that. So therefore, what is the radius then of this disk is the first question. So keep in mind the height is the thickness here. So wouldn't it just simply be sine x? Isn't this the actual radius then in this case, if the disk is made from a revolution of this region? Okay. Remember, this is the whole disk right here. It goes into both quadrants, both first and fourth quadrants. Okay, that means half the disk is ultimately that half that distance is going to be the radius, which in our case is simply sine x. Now, what about the height? The height here is the thickness of the disk. Well, in general, that's just going to be delta x. So some change in x. We don't know how thick that disk is. We just made it some arbitrary thickness. True? But ultimately, just like in other problems, what do we want that thickness to be? We want it to be infinitely small. And so therefore, when we write our integral now, we're going to have pi r squared dx. So in integral form, the delta x, the thickness, becomes dx. Okay. Now, what about the limits here? Okay. If we're going to sum up all the disks from here to here, we're ultimately going to go from 0 to pi. True? And with that, we can find our answer. So unless it says analytically, which I don't believe it does in any of these, we can just go ahead and use our integral command here and do our sine x all squared Alright, and so if I do my sine x all squared from 0 to pi, I get that. And we can see if that turns out to be a fraction. It may or may not, depending on how complicated the...
If you multiply that by 5,
say that again?
it's pi out in front of the integral.
Right. So this itself is just the answer to the integral part. Okay? And if I multiply that times pi, I get that. We might recognize this as actually pi over 2. Okay. And so if I had pi over 2 times pi, it'd be pi squared over 2 then, in the exact form. Like I said, ultimately, unless it says do it analytically and on the AP test and so on, okay, a decimal answer is going to be acceptable here as long as you show this part. Okay? This is the part that they're after, that you can show the setup, okay, and that you can show an answer. Okay? Like I said, on the calculator part, they're going to just assume that you use your calculator. You wouldn't have to do that by hand at all. Okay? And if you do have to do it by hand, it's going to be a fairly simple integral to deal with, because this one would not be so simple. Okay, questions on the disk method? Alright, now what makes that a little bit different is if we take that same region and I tell you that I want you to revolve it around the line y equals -1 instead. Okay. So, again, this being my shaded region, if I take a slice of that region and I revolve it around the line y equals 1, let's think about what's going to happen then. Ultimately, if I were to draw this and try to draw it in 3 dimensions, which again, it's difficult here, but ultimately my shape is going to look something like that, isn't it? On the other side. Okay, ultimately, it's going to be that same kind of shape, but what's going to be in the middle of it? There's going to be a big hole in the middle of it, isn't it? Okay, remember, if I take this and I go around the line y equals -1, there's going to be a hole in the middle of that shape. So it's going to be similar to this one, but there's going to be a big hole through the middle of it. Okay? And ultimately, in my cylinder, okay, what's going to be the deal with my cylinder? Instead of a cylinder, it's going to be something like that, isn't it? Okay. All right. And so it might be a donut, but donuts are kind of thick, so we'll call it something that's not very thick, which is, if you have any experience working with tools and whatnot, we call that the washer method. Alright, and the washer method and the disk method are going to be very similar to one another. Okay? In that we're going to get a very similar shape. We're going to get almost a disk. We're just going to get a disk with a hole in it. So the question is, what adjustment's going to have to be made in order to write an integral that's going to give us the volume of such a shape instead of a disk, which is pi r squared h. What's going to be the volume of this shape with the disk with a hole in the middle of it, which again we call a washer. Okay? And ultimately the answer is this. If we have this shape, okay, its area, if you will, if this were just a 2-dimensional shape, its area would be pi times r squared minus pi times r squared. R sub 0 being the outside radius, r sub I being the inside radius. Okay? So we'd find the area of the whole entire circle, and then we'd find the area of the little circle inside, and then we would what? We'd subtract. So that's how our washer method situations are going to get set up each time. So we're going to see if we can write an expression here for the outside radius, and I want you to watch how I write the integral here. The integral is not going to be any different because we're in nx here, so it's still going to be 0 to pi. Notice that both of these two expressions have pi in them, so we can factor that out and not have to worry about the pi. We can take the pi out. And ultimately our setup is always going to be something squared minus something squared dx. Okay? Now the question is, what are these somethings? Well, the somethings in this case are going to be the outside radius, and if you go back to our picture, the outside radius is going to be that, isn't it? The distance from the function to the revolving line. Okay, wouldn't that be the outside radius of the washer? So again, the distance from, in this case, the function, which is sine x, to the revolving line And so what would that distance be? Well, we already said this distance right here is sine x, and this distance right here would be what? It's 1. So ultimately, wouldn't that outside radius just be simply sine x plus 1? Alright, and then the inside radius of the washer is going to be this. We need that dimension right there. That's going to be our sub I, which is going to be our inside radius. And so in our case, what is the inside radius of this washer?
1.
No matter where I have my slice, the inside radius is simply 1 in this case, isn't it? Question so far? Alright, so in review real quick before we actually calculate here, when I have a disk method problem, it's always going to be of the form pi r squared dx. Okay? When I have a washer problem, it's always going to be of the form pi outside radius squared minus inside radius squared dx. Okay? So when you're setting up a disk or a washer, they should look exactly like one of these. Okay? Alright, and then calculation-wise, we're just going to do calculator again. So we have sine x plus 1 squared. Okay. There we go. So that's all squared, and then minus 1. Oops. It's going to be our integrand. And we're going 0 to pi again. And you got to remember that part's just going to give us the area part. We're going to multiply that by pi when we're done. And if it's convenient, it'll be some fraction, but in this case, doesn't look like that's the case, but it's not. So ultimately, we'll just multiply by pi, get a decimal answer for it, and get 17.501. Any questions on that setup? One thing I want to point out that's very important is that that we don't do this. When you're setting up this washer method, that if you did something like pi integral r sub 0 r sub 1 I squared dx, okay, is that the same as what we have here? If I subtract first and then square, is that going to be the same as squaring and then subtracting? Absolutely not, because this right here is, that's not r squared minus r squared, is it? It's r squared minus 2r times r times the other r squared. We'd have to FOIL that if that was the case. This FOIL does not equal this, does it? Okay. So make sure you do not do this. Do not subtract the radii and then square that result. You got to square the radii individually and square that result. Okay. Now, the third method that we're going to look at here is going to be, again, we'll use the same sine x from 0 to pi. And what it boils down to, I want you to take, before we actually do this one, I want you to notice that when we have the disk method or the washer method, we're always going to get disks and washers, okay? Disks and washers when our slice is perpendicular to the revolving line. Okay? So anytime the slice is perpendicular to the revolving line, we're going to be dealing with a disc or a washer. Okay? That's the shape that's always going to be created if we use a disc or a washer. Always going to be perpendicular to the revolving line. Alright. So, in both cases, I gave you a region that's in X, and I gave you a revolving line that was horizontal. Okay? In which case, in both cases, created the slice, a slice in X that was perpendicular to the revolving line. Now, what if we ask this, though? What if we say that I want to have my slice, okay, same kind of slice, but I want to go over the y-axis instead? Okay? If I want to go over the y-axis instead, and I kind of shortchange myself on room here, but ultimately, if I revolve that around the y-axis, it would make some kind of shape like that. True? And of course, three-dimensional. It's tough to draw 3 dimensions on two-dimensional paper, but ultimately it would be revolved around this way, so that it might look like some kind of thing that has a hole in the middle of it, basically. Okay. But more important than the overall general shape is, what does the slice look like if we revolve that slice? If I take that rectangle and if I revolve it around the y-axis, and notice that the slice and the revolving line this time are parallel to each other, okay, what kind of shape would that create? Visualize that and think about what kind of shape that would create. Think about something you might have in your kitchen that might look like that shape. Yeah, it would look like a can, wouldn't it? Okay. If you took that rectangle and you swept out the area that it would go by revolving around the y-axis, wouldn't it look like a kind of a soup can with no top or bottom? True. And so if that's the case, think about what a soup can would look like. If I had this soup can here, and I took it and I cut it down here, and I laid it out, it would be a rectangle, wouldn't it? And it would have some thickness to it. True. If I took a soup can and I sliced it up the side and I laid it out flat, wouldn't it be a rectangle with some thickness? And so ultimately, wouldn't it be a prism, if you will? Okay. And so if we wanted to find the volume of that prism, okay, let's think about what the dimensions would be. Okay, in terms of this cylinder that I have drawn here, remember this is the height, this is the radius, those are the two dimensions of any cylinder. That height would be just this right here then still, wouldn't it? The height wouldn't change, that would still be that dimension here on the side. Okay? Alright. The thickness here is going to be our dx, if you will. It's going to be our infinitely thin, it's going to be just some change in x. And then ultimately here, let's think about what is this distance going to be from here to here, that bottom dimension. That's the circumference of the circle, isn't it? The circumference of the base, if you will. If we were to lay that out flat, it would be that distance from here around the circle back to here, wouldn't it? So ultimately it would be 2 pi r. Agreed? Alright, so anytime that we have this situation where our slice is parallel to the revolving line, we're going to get what we call, instead of a can, we call it, mathematically, we call it a cylindrical shell. And so what we're going to use here in this case is we're going to be using what we call the cylindrical shell method. Alright, now to generalize this cylindrical shell method, okay, what I want to do is set up a general integral here. We'll set up a specific integral in a minute with our particular example. But in general, in our cylindrical shells, okay, the general setup is going to be the following. It's going to be 2 pi out in front because ultimately the volume of this prism that I've drawn here is 2 pi r h delta h. Actually, I'm going to call it delta x because we're in x right now. Alright, delta x, we're just going to call the thickness. Keep in mind that all this can be translated to the y's also. If we have a function in y instead of x, we could do this all in terms of y instead of x as well. So it could be instead of delta x, it could be delta y. Okay, so we'll see that as we go through some of these. But ultimately, here's the general formula in any cylindrical shell problem. We're going to have 2 pi as our outside part. Okay, and then the r part here, this radius part here, is always going to be the following. It's always going to be the distance from shell to revolving line. Okay. That is going to be our r, if you will. So that r is going to be the distance from the shell to the revolving line. And then the h is going to be our height of the shell. And then, of course, the delta x becomes dx. So we got 3 parts here. We got the 2 pi part that goes out in front. We have the r part that goes in parentheses. And we have the h part that goes in parentheses because every shell that we draw is going to be of that same format. It's going to be 2 pi r h delta x. Okay? And the RH is always going to be the r part's the distance from the shell to the revolving line. The h is going to be the height of the shell. And if we follow this format every time we have a problem like this, okay, it should be fairly simple for us to fill in the blanks. So, let's see if that's the case for this first one. Well, we know we're going 0 to pi. And remember, if it's a vertical slice, we're dealing with x's. Okay? So keep that in mind. Whether we're parallel or perpendicular, whether we're using disc or washer or cylindrical shells, we're still in x here. because we have a vertical slice, we're still dealing with x, so we're still dealing with x values for our limits. We're going to have 2 pi out here. And then the distance from the shell to the revolving line in my picture right here is this right here. There's the distance from the shell to the revolving line. So what is that distance right there from shell to the revolving line? Yeah, and again, remember I just drew this at an arbitrary spot, right? So how far is it from this line to this point right here? It's just simply x. Okay? Could be I could have drawn that slice anywhere. So in this case, my shell to revolving line is just x. What about my height? What's the height of the shell, which is this dimension right here? It's the function. Okay? In this case, it's sine x. And the thickness is dx. And ultimately, that's my integral. So, to answer it, I'm going to have 2 pi times something. Let's find out what our answer is here. We do our math 9. Oops. And we have x sine x this time as our integrand. 0 to pi. And it looks like pretty nice answer there. Looks like it's pi, right? And again, whether we recognize it as pi or not, 2 pi squared, I guess. We could also give an approximation here because it's generally going to be a calculator problem. So if we multiply that by 2 pi, oops, 19.739, and that would do it. All right. Now, these ultimately, these kind of problems are kind of like riding a bike. They're going to take some practice for just starting the setup part, but if you follow the general setups that I've shown you, okay, then hopefully that'll make it a fair amount easier. I want to do one more cylindrical shell problem here with this same region. So this time what I'm going to have you do is we're going to do 0 to pi again, but this time I'm going to have you revolve it around the line x equals 2 pi. So we're going to take this and we're going to revolve it way over here. So ultimately, if I were to kind of visualize what that might look like, I would have these two parts, and I drew this one obviously too small. But regardless, what kind of shape am I going to have if I use a vertical slice here? I'm going to have a cylindrical shell. True. My equivalent cylindrical shell will be over here. And either way, my setup is going to be exactly the same. I'm still going 0 to pi because again, the limits come from the region that we're working with. We're going from 0 to pi. Okay. We got our 2 pi. And now here's where we have to do a little bit of thinking. What is our distance from shell to revolving line? Keeping in mind that the shell is over here, and the revolving line this time is over on the right. Okay, so how far are those two from each other? Remember, these two right here were what? Those two are x. The whole entire distance from here to here is 2 pi. So ultimately, what would this distance be here then? It would be 2 pi minus x. So we go 2 pi minus x. That's our distance from shell to revolving line. That's represents our r. And then our height here, the height's still just going to be sine x, isn't it? Thickness dx. And then from there, it's a calculator problem. So punch that in the calculator, multiply by 2 pi, and you're going to get your final answer.
What does that one look like?
Really, would it look much different than what this one did? Except for there's going to be a bigger hole in the middle of it, isn't it? And think about why this one's probably going to be more. Because this one's going to kind of sweep out of the paper at us even more than the other one did. Okay, this one just kind of stays close. This one's going to sweep out an area that comes all the way out, 2 pi with a big 2 pi hole in the middle, if you will. So we should probably, well, it'd be pi to get to here and pi to get to here. So ultimately that hole would be 2 pi in diameter, wouldn't it? That's in the middle of those two. Okay. All right, so like I said, ultimately after that, it's a calculator problem. Punch it in and see what you can do. So, like I said, our homework assignment is just going to be working with some different regions and doing some revolving around some different lines. So we're working on those for tomorrow. Tomorrow we also have a couple binder problems, I believe, on our homework list. So tomorrow we will review and go over some questions and take a crack at these and see how you can do.